Good afternoon. Any question? So I saw a posting on Piazza saying, how can you track your leg days? Um, the only easy way for me to do is to expose everyone's leg days, and I wasn't doing it because some of you might have privacy concerns around it. I certainly do not have the time to individually send you emails with your leg days. So that's where it stands. Just to get a sense, any one of you would object if I were to put a spreadsheet with your name and date days against it? Okay, sounds like so I'll do a little poll on Piazza, and if anyone objects, I won't do it. Otherwise, you can always go to Great Scope and see when you submit it and get your latest back. Okay, so um, the topic today we are going to start on new topic. So we saw a fair bit of in the timing lecture that how well or how fast can a sequential system can a digital system go. What we are going to talk about on this one is how we can design them to be faster. So of course, one way to make a system faster is to use faster gates. So that's what's kind of obvious. But the question also comes up: are there other things we can do so that intrinsically our design is faster? Oftentimes, perhaps with other trade-offs as well. So intuitively, besides using faster hardware, a second approach is to use multiple copies of the hardware, namely parallelism. And that obviously comes at a cost because you have to have multiple copies of the hardware. And the other thing is, in many cases, your algorithm may not be one where there are multiple parallel things. Some things are, like for example, I don't know if I have to do some vector or matrix type manipulations and all, there often is a high degree of parallelism out there. But a lot of stuff does not, just a sequential execution of things. So the other technique is that of pipelining, and that's what I'm going to talk about out here. But very broadly, faster stuff, parallel stuff, and pipeline things. I mean, these are kind of three broad strategies. Of course, the fourth one, which has come up with a better algorithm. Okay, but I'm assuming that that sort of goes without saying. Okay, so pipelining is what we're going to talk about, and um, so. How does this whole pipelining, parallelism, and all kind of fit into the design process that we kind of indicated that if you're using things like Verilog and EDA tools and all, one ends up following. So essentially, kind of you start out with some sort of a specification of what you want. You want this input, that output, might be given some timing requirements like min, max delays and all between some action and corresponding reaction that the system's producing. And then you kind of go through this exercise of kind of figuring out how your system is going to interact with the outside world and all. And then the other thing that you do is come up with kind of an algorithmic strategy. And what algorithm is preferable partly depends upon your constraints. For example, it might be that some algorithms need certain type of computation that you cannot afford to have. Like, for example, maybe you don't have access to a divider, or maybe you do not have access to lots of memory. Those kind of constraints might also come into the way. So you kind of go through this phase where you're trying to match your algorithm, constraints, come up with an architecture to implement that algorithm, and then kind of refine that process. So somewhere in this mix of things is also this process of optimizing the architecture. So for same algorithm, I can have multiple ways of realizing it. I can certainly implement it as a purely sequential thing, much like you might do in a standard C or Java program where kind of things go in sequence. But even in the software world, we go through this exercise of saying, okay, could I put multiple threads at work to speed things up and all. Now, hardware is already insanely concurrent in the sense each gate is something running in parallel with another gate. So using hardware, uh, approaching hardware with the architecture mindset that you might do in software is not very advisable because software is more sequential and going parallel tends to be a deliberate exercise, whereas with hardware, you're starting out with something which is already deep down is parallel. And so how can you kind of exploit that concurrency that already exists? So that's what we're going to talk about. And so you kind of play with the architecture, and there are many systematic ways of doing it. Some of these things EDA tools automatically apply for you. Some of them you may have to direct the design towards. And then, of course, you build the stuff. Okay, so um, as I mentioned a few moments ago, uh, philosophically, ignoring the better algorithm and better gates part, there are two things that you can do to make things faster. Do things in parallel and do things in pipelining. Pipelining revolutionized manufacturing. In fact, it's considered to be one of the big innovations in manufacturing, which is what Ford did when it came to automotive manufacturing, kind of the concept of assembly line, which is exactly what this pipeline concept is. So parallelism basically boils down to somehow identifying that there are operations in my system which can be done in parallel because maybe the output of one does not feed into the input of the other. Okay, so I can afford to do them in parallel, and then at some point I have to bring things together. Pipelining, on the other hand, is this idea that we take a task which is sequential but divide them into stages, and then different people are doing different stages at any given point in time, and they hand over the task from one to another. So we'll see how that plays out, and they both have their roles. Pipelining has the advantage, as you'll see, that the hardware doesn't grow up that rapidly. You don't need multiple copies of the hardware. The flip side is, though, it does affect the latency. Parallelism sort of offers complementary advantages. So, um, so the assembly line analogy kind of holds true that faced with the computation task, where I have to do a sequence of things, and we already encountered many cases where we were doing a sequence of things, like our adder was like that. We first did bit number 0, then bit number 1, then bit number 2, in a sequence like that. And since they were in a sequence, I could not do them in parallel. I couldn't do bit 0 and bit 1 and bit 2 in parallel because I had to wait for the result from the previous stage. So this is where pipelining comes to rescue. That while bit 0 is doing addition of a pair of numbers, the hardware for bit number 1 might be working on the addition for the previous pair, and so on and so forth. So the idea is that I'm not doing the task just once. I'm doing repeated addition. So I have pairs of numbers arriving, and while one stage is working on one pair, another stage is working on a different pair, and so on and so forth. So that's the concept that happens in manufacturing, that a car flows through the assembly line, and at different stages, different things get done. So within the assembly line, at any given point in time, many cars are in different stages of production. Same concept out here, that if I have a computation to do, but I have many copies of it to do, then I can organize things that different hardware are working on different tasks, which all of them are trying to perform the same computation. So, taking our adder example, so we can think of this otherwise this bit serial adder, this ripple carry adder as one where the stages of work are corresponding to the different bit positions. So we start out from bit 0, it does its job, produces its output, then it flows to bit number 1 and bit 2 and bit 3 and so on and so forth. So in normal approach, we come up with a pair of numbers, and this whole computation flows through from bit 0 to the most significant bit, and once it is done, then we move to the next numbers. Okay. Now, if you think about it, sort of insane that while bit number 10 is working, bit 0 through 9 have already done their work and they're sitting idle. And likewise, while bit number 10 is working, bit number 11 through n minus 1 are just waiting for the work to arise, right? So this kind of way of doing things has the disadvantage that at any given point in time, only one of the n bits are active. So you can say that my hardware is active only 1/nth of the time, which is kind of a waste of an otherwise sort of useful, otherwise perfectly fine sort of set of gates out there. Now in software, in the world of computers, we don't worry about it, that issue of wasted hardware so much, because there's always something else for the computer to do, right? So there are lots of applications and processes and things running in the background, so the operating system kind of juggles among them. Hardware is not like that. If bit number 0 is not doing that addition of the 2 bits, then it has nothing to do. So it's basically going waste. So this is where somehow orchestrating things so that hardware is fully utilized, and of course we also benefit from speed up out there. So what we can do, for example, is we can say, okay, let's look at this hardware to be composed of multiple stages, and for the sake of argument, let's imagine that we have stages of 4 bits each. So we have a cluster of 4 bits, it works, its carry out comes out, feeds into the next stage, and so on and so forth. You could imagine, the argument I'm making, you can imagine even at a single bit level, but sorry, so I'm using 8 bits out here. So 4 groups of 8 bits, but you can imagine the same argument right down to a single bit level. So I'm viewing this adder as made up of 4 stages, and now this is what I can do. What I can arrange for is that imagine as if I have a sequence of ABs coming. Okay, so every clock tick, a new pair of A and B comes. And what we will do is we will organize our adder so that we put these registers out here. Now, recall the registers really serve at delaying the input by a clock tick, right? So the input to the register moves to the output at the clock tick. So we had seen that example in one of the lectures where I had a series of flip-flops, and the input was moving from one to the other in kind of at every clock tick. So what will happen in this figure is the following, that a pair of AB which arrives out here, in the first clock tick, all we will do out here is the lower 8 bits. And we will take the carry out and the sum which is produced and make it available as input to this register. At the next clock tick, both the values produced by this lower hardware as well as, so these values as well as the values which are coming out here, which are for this particular pair of AB, which are the upper 24 bits, they will all, so if clock number I is out here, then at clock number I plus 1, the same data will move to the next stage. And in the next stage, it will work on the other remaining 8 bits, the next 8 bits. And the same logic. At cycle number I plus 2, the sum that I had produced, the result of this stage and the upper 16 bits, that will move to the next stage of hardware. And then this stage will perform its work, and then it will work and will come out then. So originally, what was a plain combinational logic, now we have split it up into 4 stages, corresponding to each one of those 8 bits. So on the face of it, it seems like a bad deal. What I was doing in 1 clock tick, I'm now doing in 4 clock ticks. Granted, while the original pair was being handled by stage 2, I can begin to process the next pair. But it sounds, looking at this, as if uh, to add, if I'm looking from just a single pair of numbers perspective, then it's now taking 4 clock ticks. What do you think? The delay seen for adding these two numbers is certainly going up in clock ticks, but do you think it is also going up in uh, the time taken, number of nanoseconds or whatever? So what decides the clock tick size? Let's go back to the past couple of lectures. So what dictates how fast the hardware can run?
Time for the, in this case, for each adder to finish.
Okay, so combinational delay, the largest combinational delay from flip-flop to flip-flop, right? Originally, it had a 32-bit adder. So it would have if it had flip-flops on either side, let's say, then the clock delay would have been the delay, clock period would have been the delay of the entire 32-bit adder. But now I have chopped it up into finer pieces. So flip-flop to flip-flop delay now is the delay of each stage. And roughly speaking, ignoring overheads, it would be 1/4. So while it is true that I'm taking 4 clock cycles, but because my adder is now chopped up into finer pieces, each one of them offers a smaller amount of combination delay. So if all I'm looking at is this adder, let's assume nothing else in the system is bottleneck, then I can run the system potentially at 4 times the clock speed. So my clock number of cycles to do an adder goes up by 4, but my clocks are 4 times faster, and therefore seen from the perspective of a pair of AB, it should be the same amount of wall clock time. It's just that I'm running the system faster. And by the way, every clock tick, I can handle a new pair of AB. Okay, so whereas previously, I had to wait for the next pair, to process the next pair of number until I was done with all the 32 bits. So what's happening in this case is I'm increasing the throughput of the system. So let's imagine my adder was 100 nanosecond, 32-bit adder. Previously, every 100 nanosecond, I could handle one pair of AB. Now, every 25 nanoseconds, I can handle one pair of AB. So my throughput goes up factor of 4. Moreover, for a given pair of AB, previously I took 100 nanoseconds, now I take 4 times 25 nanoseconds. So still 100 nanoseconds. Now I'm ignoring issues out here, and we'll see shortly that these registers obviously are not ideal. They offer some additional delay and all, so we pay that. We are also adding registers, so that's costly. So I'm certainly paying for all of this and some additional hardware and some not quite linear speed up, so there will be some penalty for that. But seems like a good deal overall, right? I mean, by inserting these registers, I'm basically improving the throughput of the system considerably. The other way, obviously, would have been to have 4 adders, right? 4 32-bit adders. So here, in all likelihood, registers are going to be cheaper than your adders, and therefore you sort of come out ahead. So this is pipelining at work in a very simple sort of example. Any questions on this? Is this concept clear? You might have encountered it in some CS31, 32, 33 possibly, but any questions before I move to the next? Okay. So again, to emphasize out here, clock goes up. So clock frequency goes up, area goes up because I have registers and stuff like that. Latency goes up a teeny bit because registers add some delay, and throughput goes up. So that's kind of the set of trade-offs that we are kind of seeing. And there's one final quantity, power. Uh, Power goes up because I'm doing a lot more work. But energy per operation remains the same. So, in terms of how much energy, how many joules I'm going to spend per operation will be the same. But since I'm doing more work per unit time, so the power does go up. Okay, so that's what's happening. And in fact, this kind of pipelining is really the magic behind uh, sort of the processor frequencies which headed into gigahertz and stuff like that. The modern processors are extremely deeply pipelined. Okay, you may have 20-stage pipelines. Okay, kind of pretty deep pipelines. Okay. Um, there are challenges with this kind of structure also. Can you think of any? Like, so I gave you the positive side of the story. My throughput goes up, factor of n and stuff like that. And I talk. So let me also write down: power goes up, and energy per operation remains flat. Okay. Uh, what kind of challenges do you think in using this approach in designing? Can you always make use of this pipeline structure? Like under what circumstances, like for pipeline to be effective, I need to be able to feed stuff into it. So, so take the analogy with like car manufacturing, pipe assembly line, multiple stages. What kind of things can cause the pipeline throughput to be not what we think it should be?
There's like an equal amount of time taking. So like
Okay, so if different stages are of unequal time, right? In this case, all the stages are identical, so they take the same time. But it could be, taking that analogy, that one of the stages takes more time, and that becomes the bottleneck. So other stages will still lie idle, right? Okay, so that's one. What else? What about my ability to keep the pipeline full, right? I mean, that's the other thing. If the data to be processed doesn't arise, so that in the car analogy would be if one of the upstream vendors supplying Toyota doesn't ship the part in time, so now suddenly you have a bubble in the pipeline. Okay, the bubble will kind of flow through your manufacturing line because there's nothing to do. So that's another issue. You have to make sure. Okay, but the final one is a nastier one. So imagine that uh, I'm doing some operation, and the result of that operation is going to affect the next operation. Now, normally, when I was doing one operation at per clock cycle, that was straightforward. I do the operation, look at its result, I decide what happens in the next clock cycle. What would happen here? So I have two operations going, not specifically the adder example, but imagine that I have a pipeline where the what I do with the next pair of inputs depends upon what happened, what the outcome was for the previous pair of previous input. Do you see a problem in a pipeline situation?
You won't necessarily know the whole output of the previous input before the next input comes.
Right, and so I cannot start on the next input before the previous input is right. So anytime I have a situation where I say take the processing of one pair depends upon the outcome of the previous pair, then my pipeline strategy breaks down. So if I say something like if something, then do this, else do that, very common in algorithms, this strategy won't work because I have to wait for the outcome. That means my pipeline is going to basically sit idle. So dependencies across inputs cause problems for pipeline. If inputs were just independent, I can just keep feeding. But the moment there is a dependency, then that begins to cause problems. So let's uh, uh, look at this example in terms of what might happen. So at some point in time, I have the 0th pair arriving, and I have now computed the lower sum, and the upper sum is as it is. Next stage, the 0th input has moved to the second stage, and the next pair of input, which we are calling as 1, is what the first stage was processing. And next clock take further movement, and that process will keep sort of moving like that.
Can you explain again why the clock frequency will increase by doing parallel?
So what decides the clock frequency? Again, so remember, the clock frequency is decided by, for every flip-flop to any other flip-flop, what the combinational delay was. Recall that setup timing constraint, which we saw last lecture. So what it means is that the frequency of the clock is determined by the worst case path through my circuit, which starts at a flip-flop, goes through combinational logic, and ends up at a flip-flop. Okay? If I had my entire adder sitting as a single monolithic block, then I'll have to traverse from bit 0 to bit 32, all the entire delay. Whereas by breaking it up like this, my paths only extend from bit 0 to 7, 8 through 15, 16 through 23, and so on and so forth. So my combinational paths have been chopped to 1/4. So assuming there was no other bottleneck path elsewhere in the system, that would mean that I have sped things up by a factor of 4. Does that? Okay. Any other question? Okay, so let's examine then precisely this, so what this question asked just now. So what's happening to latency and throughput and stuff like that in a pipeline? Okay, so just to make sure we understand latency and throughput. Latency means from the point an input arrives to the point its result is known according to, like, you measure it against your wall clock time, okay, or whatever, external time, so many seconds, so many nanoseconds. Throughput, on the other hand, refers to how often can I produce a new result. In a sequential system, latency and will dictate the throughput, because if it's sequential, I'm going to be processing things one at a time. So if my latency is 100 nanosecond, then after taking an input, the next time I can accept an input is 100 nanosecond later. So in a purely sequential system, by the way, here I'm using the term sequential in the sense of non-pipeline, non-parallel, not sequential digital system. Okay, so that is not pipelined. Okay, in a purely sequential system, throughput equals to 1 over latency. But because of pipelining, this, if I have an n-way pipeline, then in that course of latency, I will actually be able to feed accept n inputs. So my throughput increases by a corresponding factor. If I have a 4-stage pipeline, then my throughput goes up a factor of 4. My latency, as measured by clock ticks, goes up, but my latency as measured in nanoseconds, or whatever absolute time, does not go up, or does not go up proportionately at least. So let's imagine that before pipelining, the delay of our 32-bit adder was 3200 picosecond. So in that case, the adder could have solved one problem each 3200 picosecond, and that would mean that it can do roughly 312 mega operation per second, million operation per seconds. If I were to pipeline it the way sort of we talked about, then we expect the latency and all to go up. And thus far, I was hand waving my way through, saying, okay, four-way pipelining, so I'll have a improvement of 4. I was ignoring the effect of putting those registers and all. But these registers, as we saw in the previous lectures, do come with their own setup time and delays through the flip-flops themselves. So we have 3 things to worry about. TDCQ, which is the delay in the register from clock to the output. TS is the setup time. Remember, that was in our equation. And let's see who remembers. What is TK? Huh? Skew. Remember, that was another nasty bit that we had. Clocks not reaching all the flip-flops at the same time. So that was also eating into our clock budget. So in this particular example, 100 picosecond flip-flop delay, 50 picosecond setup time, 50 picosecond skew. So I have a 200 picosecond extra overhead per stage. And I have T stage, which is the delay of one stage, which in our particular case is 800 picoseconds. So, and n is 4, so in our particular case, it becomes 4 times 800 plus 200, which is 4000 picosecond. Okay, and so the latency through the whole system previously was 3200 picosecond. Now it has gone up to 4000 picosecond because I'm paying this additional delay corresponding to the 4 registers. But it has not gone up 4 times, even though we are taking 4 clock ticks. Okay? And the throughput would now be 1 over 4000. Okay, because every that's my clock tick, and every clock tick I'm able to afford one additional pair of input. So my throughput will not be quite 4 times; it would be smaller, but nevertheless big improvement. Okay, so one has to sort of account for this thing, and as you might imagine, if I pipeline too much, then at some stage it becomes a losing proposition because the delay is added by the registers are whatever they are, 200 picosecond, and meanwhile I'm chopping the adder finer and finer. In this example, 32-bit adder, so it was 100 picosecond per bit. Well, 100. If I were to chop it down to 1-bit pipelining, then my 1-bit delay is 100 picosecond, but my register would be eating 200 picosecond. So my stage would be 300 picosecond in that case, and that would probably not be a good deal because register will be a very high fraction of the overhead. So if you were to plot n, which is the number of pipeline stages, versus throughput, you would see that it's not linear, it's not a proportional thing, okay, in the sense that as I increase the pipeline, it's not as if I'm seeing a corresponding proportional increase, but it will kind of start grouping at some stage, and at some stage, further pipelining may actually worsen things also. So deep pipelining, in addition to the problems we discussed earlier, that I may have a challenge keeping the pipeline full, I exacerbate my problem of dependency across inputs and things like that. But the other reality would also be that the overhead of registers will begin to dominate, and I will not see any gain. The equivalent out here is that in a manufacturing setting, there is a handover cost, right? I mean, when at every station there is work being done, but when the car moves from one station to another, there is a transit time, and that is the equivalent of our register overheads in that analogy. Okay, so if the transit time was too much, then having too many stages in my manufacturing process can reduce the efficiency. Same thing going on out here. So I mentioned pipelines are also used by processors. The pipelines are used very commonly because that's probably the most effective way that we have for improving performance. So if you look at computers, pipelines are certainly used inside logic blocks which tend to be very complicated, like adder, and certainly for multiplier and dividers, because they are, if we were to run them as entirely combinational blocks, then the clock cycles would be very slow. But additionally, even when you pop up at a higher level, a computer also does several tasks in sequence. So when you run a program, your assembly instruction comes through, it's fetched from the memory, it is decoded, it is executed, and its results written back to memory or register, right? So there are kind of these different phases involved. And again, in a simple processor, what I might do is I might do all those phases for one instruction before moving on to the next instruction. So fetch, decode, execute, put the result back, and again repeat the cycle. But nothing says that it has to be like that. I can, when I fetched an instruction and then I started decoding it. Meanwhile, while I'm decoding instruction number I can start fetching instruction number I plus 1. So I can do that pipelining to improve the throughput of the processor. So again, processors face the same issue. So they can work on instructions in a pipeline fashion like this. They can work on instructions in parallel, which is they can say, let's fetch 4 instructions and start working on them in parallel. So both options are available, and they again come with their trade-offs, and processors use both of them. So pipeline and the parallel stuff is usually called superscalar processors. So within a processor, they will have multiple execution units so that they can run on each one of them. And then, of course, there are other forms of parallelism. We have processors which have multiple cores, and then you have computers which have multiple processors, and then you have clusters which have multiple computers, right? So at all levels, we have sort of parallelism which comes up. So what the slide is showing is that how we can have these, starting from my program counter or instruction register, I can have all these different phases of fetch, read, ALU, mem, deal with the memory, write back, stuff like that. So there are these different phases. What the specific phases are doesn't really matter. Depends on processor. But the main point is instruction 1 is fetched. Then while instruction 1's data inputs are being read, the next instruction 2 is being read. And then while instruction 1 is then being processed in the arithmetic logic unit, instruction number 2's operands are read and instruction number 3 is being fetched, and so on and so forth. And this is where you can see the problem that pipelines present. If instruction number 2 said, if instruction number 1 was add 2 register values, 2 variables, and instruction number 2 said, if the result was negative, do something. Well, clearly we have a problem because the result is not available until out here for instruction 1, and meanwhile I have to worry about what to do in instruction 2. So what would happen in that case? What do you think? What would the processor do? There is an instruction which needs the result of the previous instruction. Yeah.
Just wait until.
Just wait. It has to stall the pipeline, right? Because I don't have the data I need. I cannot proceed further. So in essence, essentially now nothing would be done, and you can think of it as like a vacuous task or a bubble which gets inserted and kind of flows through the hardware. So hardware is idle in that case. So conditional things like if then else, for loops, while loops, these kind of things, anytime I have a jump of some form, potentially creates a problem for a pipeline kind of architecture. And the deeper the pipeline, the worse off you are, right? So even something trivial like I mentioned that multipliers are often pipelined. So in many processors, you might encounter things like if you do a multiply, the result of the multiplier are not known until 2 or 3 clock cycles later, because that's an indication that there is a deeper pipelining going on out there. So pipeline creates this kind of unfriendliness there, but that's the only way you can sort of deal with it. Yeah, if you're using pipeline to push the speed up, then that's the penalty. Another place where pipeline gets used quite a bit, I know many of you are fans of games and stuff like that. Probably the most compute intensive part of your normal computers are the graphic processing unit, the one handling all the images and videos and stuff like that onto your screen. And really, the graphic processing unit is a large number of processors, simpler specialized processors working in concert to sort of keep your pixels supplied with correct data. And pipelining is used again. So besides parallelism, pipelining is used very extensively in these graphic processing units. And so usually on the way to the final pixel, we kind of start out with some higher level things. Okay, I mean higher level objects which are shaded, the lighting is taken into account, overlap between objects, all that stuff is done in the hardware. So over time, like if you go back 30, 40 years ago, programs used to write pixels directly. But now in GPUs, we feed data in terms of much higher level objects. Okay, in fact, game engines and all kind of make use of that fact that there's a lot of physics of those objects you see in the games and all are modeled and simulated and handled within the graphic processors. So there is a pretty complicated sort of a pipeline which kind of or stages that exist, and again it is chalked up into a pipeline because that is how they can keep the things refreshed. There's very little time. Usually we display things 30 frames per second. In gaming-oriented computers, the refresh rate is usually larger, usually faster, maybe 120, maybe 240. So you have relatively little time to do some pretty complicated processing. Okay, and with things like virtual reality and augmented reality and all, the load on these GPUs is just going up and up and up. So large number of processors and deep pipelining is how sort of they pull through that. Okay. Another place where pipelining and where the need of speed is very high is the communication systems. Both your cellular radio, your Wi-Fi radio, as well as your wired network interface cards and all. So one place where this is seen very dramatically are the routers which are sitting in the backbone of the internet, and they handle multiple tens of gigabytes or terabytes of data kind of flowing through in a short period of time, lots and lots of packets coming in. They have to examine the packet, figure out how to route them and stuff like that. So again, this kind of processing is not done with a processor running software, read a packet, process it. These are hardware packet processing engines, sometimes specialized processors, a lot of time FPGAs. And again, we rely on sort of all sort of different stages of packet processing are done in a pipeline fashion. Okay, both as the packet comes in and as the packet goes out. So I guess the point I'm trying to make is that there are lots and lots of systems where high performance is needed, and pipelining and parallelism, of course, are another two tools in one's arsenal which one can use. There was a Piazza comment about why do we bother with things like FPGA? Why not our good old microcontrollers and Arduino and stuff like that? The performance levels are dramatically different. Okay. Again, the point to note is your processor does in a single clock cycle a logic operation, an AND. Your FPGA in that same clock cycle can do millions or tens of thousands of ANDs. Okay, so the potential is there because all that stuff is sitting there ready to work in parallel. The challenge is orchestrating it is hard. So hardware design at that level is harder. Parallelism and pipelining are not easy once you are dealing at that low level, but the performance advantages that you can get are obviously tremendous, even at the same clock chip, right? I mean, a microcontroller A modern microcontroller, like the ones you find in Arduino and all, are probably around 20, 30,000 gates, ignoring the memory. But all those gates go towards executing one instruction every clock tick. Whereas if you had the same gates and you were designing them, you can certainly do a lot more than one instruction per clock tick. And that's really what it kind of boils down to, that for same speed, I can get away with fewer gates, or for same number of gates, I can have a lot more performance. So really high performance, really high performance applications tend to move away from processors to designing at the level of hardware and hardware level parallelism and stuff like that. Some of the supercomputers, some models of Cray and all, are actually just FPGA things that you can program. Then in many cases now, FPGAs are put as accelerators next to general purpose processors. So for example, Microsoft in its data center has FPGAs next to the servers, and you can make use of that as part of their cloud service, which exists for this purpose. So the challenge has always been, can we make the programming of these things easier and simpler? So issues with pipelines. Many of these points have come during our discussion. So one is load balance. If one stage takes longer, then every other stage suffers, because my clock cycle will be dictated by the worst case stage. Many a times, you don't have a choice. You cannot pipeline arbitrarily, or it would be too costly to pipeline, because in pipelining, what we're really doing is, what was an ordinary wire, I'm now putting a register out there. And there are many reasons why you may not be able to do that. Oftentimes, the hardware blocks you use are you purchase from other companies, and they give you either a physical design that you just put down in silicon, or they may give you Verilog, which is highly obfuscated, or they may give you Verilog and they may say that legally you cannot tamper with it. Okay, so any number of reasons, and therefore you cannot pipeline things away. You can only sit at boundaries that you have access to. So that's one issue. Variable load across data. It's very common that hardware delays are data dependent. Your multiplier may take less time when multiplying by 0, let's say, versus when it is multiplying to arbitrary numbers. And it would be desirable if you can somehow make use of that. Now, what may happen is, if there exists some small fraction of your data values where the delays are long, then your whole pipeline, again, your whole clock speed is going to suffer as a result of that. And then finally, longer latency. We did see that the latency did go up because of the register delays and all. So while it doesn't go up by factor of n, it does go up because of that added factor. So there is an impact on latency which one needs to sort of worry about also. So pipelining comes with challenges, makes the whole design process tedious, but is oftentimes worth it. Yeah, I'm going to skip this part. Okay, ignore the rest of the slides. Yeah. So basically, the issue, the opportunity with pipeline is that I can take tasks, deviate up into smaller chunks, benefit from the increase in throughput, and hopefully keep the increase in latency and all bounded. Pipelining do introduce this issue that data dependencies across successive data inputs are harder to manage, but nevertheless they are extremely powerful and beneficial. Any questions before I move on to the next topic, and that would be the last topic of the course. Okay. So the other thing I want to talk about is some issues that arise bunch of issues that arise when you think of when we deal with digital stuff at an even higher level. So for most of the course, our view was we were designing part of a chip or kind of right at that low level, but these chips and all obviously sit in a more complicated system, and there are a bunch of issues that arise out of that. So I want to touch upon some of these things, specifically these three topics: interface timing, that is what happens when we interact with the outside world, interconnect, and memory. So one challenge that we face often is how do we pass information from one digital system to another digital system. So within a chip, the output of one module goes to the next module, and we have those set up hold time requirements, and we are done with it. But oftentimes these chips need to interact with the outside world, and the outside world may not be operating on the same clock cycle. In fact, it may be on a totally asynchronous clock cycle. And we saw that it does present challenges of not being able to meet setup and hold times and all, but there is also the challenge that how do we get the data out? One of the costly things around hardware is I can move lots of data within the chip, but for data to go outside the chip, it has to go through pins, something mechanical. And all those pins and all which are sitting at the periphery of the chip or connectors on your boards, they take area, they take volume, they are sparse, so they present a lot of challenges. And also, they are slower. And also, they eat up a lot of power. In a modern chip, maybe a good 50%, in a modern computer system, a good 50% of the power just goes in doing I/O, okay, just moving data around, not actual computation. So being able to do interfacing properly is quite important, and a whole set of issues come up there. So what are the common ways we get the data out of our computers? Anyone? What are the kind of standards or buses or interconnects do we see in our modern computers?
USB.
Okay, USB is one. How fast does USB go? Anyone?
Like 5 or 10 gigabits.
Not quite there yet, but okay. So original USB was, I think 10 megabit or something like that. Then USB 2 was nominally peak of 480 or so, and USB 3 is into a few gig. Okay, but not that high. What else? What other things do we see? Ethernet. How fast does Ethernet go? Huh? 1 gigabit is the common one. There is also 10 gig out there, which is used in data centers and all. It's very unlikely that you will find it there, but there is 10 gig. What about Wi-Fi? How fast does it go? No idea. Okay. What about cellular? How fast does that go? So modern Wi-Fi, the latest standards are around a gig now. Okay? Cellular, in theory, now some of the phones have chips which go up to 400, 500 megabit, but whether the carrier support it or not is pretty clear. The point I'm trying to make is that there are these pretty high-speed interconnect capabilities that do exist. And then on the other hand, we also have very slow stuff like serial ports and stuff like that, okay, which are insanely slow. One thing you would see is that a lot of these interconnects are serial. They send the data one bit after another on the same piece of wire, as opposed to parallel ports, which used to be in fashion in 80s and 90s, and I guess in the PC world for another 10 years or so after that, but now they're extremely rare. One might think that parallel would be good. Multiple pins carrying data would be a desirable thing to have in terms of speed. There are two issues which come in the way. One is, of course, more pins, thicker wires, and all, so that's a problem. But the other issue actually is that we can pump data faster on a serial line than on a parallel line. Now that might seem ironic, but the reason is the following. When I have a parallel set of wires running, when I put a bunch of bits on them, my 32-bit word, and then that 32-bit word traverses over the wires, reaches the other end. At the other end is a register, and they're going to clock it in. I have to make sure that all those 32 bits traverse roughly with the same delay. Unfortunately, long-running traces or wires of interconnects, the delays can be very asymmetric. Since they can be asymmetric, it's kind of like a skew, so then we have to budget for it, and that becomes a problem. So it's much easier to send data at a high speed over a single wire, because then I have to not worry about the skew between bits. Okay, so you would see that our high-speed interconnects are all kind of serial. Okay, just pump things out. So going back out here, I have a sender, I have a receiver. These could be two things from my chip. These could be two separate chips. These could be a chip on one board and a chip on another board, and they are sending out some sort of a data, some sort of data that they have to send out. So there are several issues that come up. One is that one way is that we send data out open loop, which is the sender just keeps putting data once per clock tick or once every so often on the medium, the wire or the air if it's wireless, and the other side has to keep sort of reading it. The problem with that is that if, let's say, for example, this guy is backed up, maybe it is slower, maybe some memory is full and all, then there is no way for the sender to know about it, so the sender keeps sending stuff out. So this kind of open loop strategy, that is, I'm not listening to the receiver at all, usually doesn't work very well. So there is usually some provision for flow control. Somehow, some mechanism so that the sender and receiver coordinate so that they send things just at the right speed and all. And this holds true at all layers, like how rapid my bits are going to, if I'm sending, let's say, packets of data, then how rapidly I'm sending the packets and all. And then finally, the part which I said serialized. We tend to send data bit after bit as opposed to multiple bits in parallel, because timing becomes a pain when we send bits in parallel. So we kind of serialize things and send them out. So, and a little bit of these issues we are seeing in design assignment that I handed out, number 3, as well as design assignment number 4, that external world often is on its own time scale. Button presses and things like that may not be such that I'm getting a new piece of data every clock tick. What the external world thinks of one data item may actually span multiple clock ticks. So we have to kind of deal with those kind of issues. So usually, when you look at these interconnects, which connect to devices and are serial in nature, they'll typically have a clock, and they will have a serial data line going one way, a serial data line going another way. So if you look at USB specifications, there's a clock signal, there is a serial data going one way, serial data going another way. And if you look at most other such interconnects, they are of that nature. Sometimes they may have multiple serial data lines, but that's where things stand. So you'll have some sort of a clock, and then the data is going over it, and then there would be a protocol defined as to how this data is being encoded and things like that. So so there are different scenarios that can occur in this kind of situation. One is this notion that we say that the data is valid at every clock tick, And so something or the other is happening at every clock tick, and we are going to make some sense out of that. Another possibility is that the data is valid only at certain clock ticks, in which case I need to provide some other indication as to what those, how does the receiver know that at this clock tick the data is valid versus not. In the design assignment 3, if what we're doing, there is another signal which says data ready or data valid or something like that. So there can be an additional signal which is indicating something about whether it's a clock cycle where data is valid or not. So there has to be some indication of doing something along those lines. And then finally, if I have flow control, then the receiver has to send back something to me. So if you look at typical interconnects, which particularly those which are used within a chip or within a board, you would see a clock, you would see data lines. If it is within a board, there could be multiple data lines. So your PCI Express and these kind of slots that exist on the motherboard, they are parallel because they are going over shorter distances. So I'll have some data thing. Then usually I will have a signal called valid or ready or something like that, which would basically indicate that the sender has put valid data onto the data lines. And then what would happen is that the receiver would read the data, and kind of the idea is that the receiver may be slow or fast, we don't know. So what the sender does is it puts the data on the data line, then raises the signal up, and then it waits for the receiver to reply back saying, hey, I am done reading. So the receiver is sending this ready signal back, which is basically saying, look, I'm done. Now you can move to the next piece of data. Okay, so essentially the two parties are negotiating. And there are many different ways this protocol can be structured, but essentially data exchange can take place when there is data and the receiver is ready. Both conditions have to be met, and through this bidirectional signaling, we kind of make sure of that. And pretty much one has to do this kind of stuff because otherwise your design constraints become too rigid. That is, both sides have to operate at peak speed and all, so you cannot have cheaper devices and things like that. So this kind of handshaking is extremely common, and there are many ways of organizing it. You might read about terms like 2-phase handshake, 4-phase handshake, things like that. But common to all of them is sender says, hey, I'm ready, somehow receiver says, hey, I'm ready or I'm done, and then the two parties exchange data and move on. Now this ready and done part in buses which are on the chip, on the board, are separate lines. There would be pieces of wire or pins. But on things like USB and all, these are bits embedded in the same serial data stream. So what happens is when one device needs to send something to another device, it will send some unique bit pattern over the serial line, and the other device will know that, okay, there's data kind of coming in. And of course, on the reverse side, some similar magic happens. Okay. Serialization. Serialization refers to that instead of sending bits in parallel, we are going to be sending bits one by one on the piece of wire. And I said the advantage of doing that is I don't have to worry about bits arriving at the receiver at different times, because now they're going over a single wire, so I can never have the possibility of bits arriving. Like if I'm monitoring 32 wires, it could be, in a parallel case, it could be that on wire 1 I have value for one word, and on wire 2 I have value for a different word. When they're arriving over a serial link, they are guaranteed to be arriving one after another. So timing becomes kind of a lot simpler. But the complication now becomes is, how do I know one word has ended, another word has begun? And that is done by what are called as these framing signals. Okay, so essentially there would be some signal or some bits which will indicate that I'm done sending or I'm sending something new. So this whole I/O design, as you can imagine, requires a fair bit of low-level details and all. So some of the more complicated parts of our compute system, as I mentioned, is the stuff which goes on sort of hidden from us, but kind of these high-speed data exchanges. A close sort of cousin of close relative of this whole I/O problem is the problem of interconnects, which refers to the fact that oftentimes multiple things need to talk to each other, exchange data with each other. So, for example, in our computers, we have lots of peripherals, and they all need to kind of talk to the CPU. Memory needs to talk to the CPU. Peripherals need to talk to the CPU. So somehow we need to provision for some sort of an interconnect so that anyone who wants to talk to anyone can talk to it. Now, one way of doing it would be to have some wires running between every module. So if I have n modules, I will need n square interconnects. But we don't do things that way. So what happens there? Anyone? How do, like, when we buy these PCs in which there are multiple PCB, multiple slots and all, and still magically anything can talk to anything. So what is the interconnection pattern within our computers? Someone else? No? Anyone heard of things like PCI bus, PCI Express, things like that? Nope, nope, nope. You never look inside your computer. So, okay, I guess you are the only one. Multiplexer is how we would do it in logic, but we do it via what are called as buses. So, but buses are conceptually a form of a multiplexer, but not in the form of logic gates. So, kind of the idea. So, let me back up a little bit. What does a Ethernet hub or Ethernet switch do? Like, I'm sure you probably have one at your home, or so. What does that box do? What's the functionality? I'm not talking about how it's implemented. What's the functionality it provides? No, it has potentially nothing to do with the internet. So again, what Ethernet switch connects to different Ethernet jacks. All of them connect to the switch. Switches can connect to other switches, which can connect to other jacks. That's how you make your local area network. Question, what does that switch do? Because the problem we are talking about is analogous, right? I mean, I have n modules on my chip. Potentially, any one of them needs to talk to any one of them. And one strategy would be to string interconnect between every pair of modules that needs to talk. In our buildings or homes, the analogy would be I have an Ethernet cable running between every pair of jacks, but we don't do things that way. We connect them to these switches, and so what do these switches do?
It's a server, basically. So it helps the communication between different devices, basically.
It's not a server, although they do have computer chips inside them for sure. So a switch basically is responsible for connecting two parties. One party is sending a packet. The switch has to figure out which party is a recipient and then somehow send the packet there. The term comes from telephone switches. I pick up the phone, dial a number, some magic happens in the telephone network, and my call gets routed to the right place. Okay? So one way you could imagine I could do things inside my chip is something analogous. I could have some sort of a switch. A hardware module needs to send some bits to another hardware module. It will, instead of having a dedicated lane or dedicated wire running between, or set of wires running between two modules, it ships the data to this switch and tells it where it should go, and the switch kind of sends it. So I can have a little network on the chip. And indeed, network on chip is the term which is kind of used for these kind of architectures. So that's one extreme. I can literally mimic what happens in the internet. My computer just sends out a packet and it goes through a series of switches and routers and gets delivered eventually to the other side. So I can mimic that, but that comes with its overhead and all. So now I need to find some middle ground. So I don't want to run wires between every possible modules that need to talk, but at the same time, I also want the flexibility of anyone to talk to each other. So one very common strategy which is used is this notion of a bus. So the idea behind bus is that it's a shared wire or a shared set of wires on which at any given point in time, two modules can exchange data, like one module can send data to another module. So for the duration of when they need to talk, the bus is just used by them. So in this particular case, I have multiple clients. I have n-1 clients, and depending upon their needs, maybe at some point in time, client 0 wants to talk to client 10, another point in time, client 2 wants to talk to client 5, and so on and so forth. But they don't have a wire connecting them directly. All they have is a shared bus. And the bus, only one piece of data can go over it at any given point in time. So what would happen in a system like this is, there is this guy called bus arbiter. We saw an arbiter. What does an arbiter do?
Depending on if it's like fair or not, it'll basically just pick the first bid.
At a higher level, you're going into details. What function does the arbiter is the arbiter providing?
Basically, just picks
one of n requesters. It is guarding a resource. There are many entities competing for it. It picks a winner. Here we have exactly that situation. Bus is a shared resource. Only one, at any given point in time, only one piece of data can go over it. And I have multiple requesters, all these clients who want to exchange data. So what will happen is that these clients will have some sort of request lines running to the arbiter. Every round, you can think of a round as a bunch of clock cycles. So every so often, we'll go to the arbiter, say, hey, I have some data to send. I need the bus. And other clients are doing the same thing. The arbiter will select a winner, and then I get to use the bus for a certain duration, and then I will squirt out the data to the other party I want to talk to during those clock ticks, and then we back off. And there are many ways you can then structure the details, but at a high level, I have a bus, kind of like a highway, except that the highway is such that at any given point in time, there can be one vehicle on it or whatever, one convoy going on it, okay? And we are requesting the arbiter to do it, to manage that process. So the bigger tower computers and all, where you can plug your own boards, essentially what happens is on the motherboard, there is a bus. Exit entry points to those bus are those slots. You buy a card, a graphics card or whatever, you plug into that. And then it can talk to other things, including your CPU, of course, but cards can talk to each other. So you may have a high-end RAID controller for your hard drives. Maybe you can have some graphics card. Maybe you can have some sort of a motor controller, and because maybe this computer is controlling a robot or a car. So there are boards you can plug in, and each one of those represent the client. What the standards define are what the protocol for talking over those wires is, and what the arbiter does. And there are standard buses out there in the industry. PCI bus the reason I mention it is because the most common bus on the on our normal computers, there is something called PCI Express. So you can buy cards for standard PCI and PCI Express. On the industrial side, there are other standards like this, but they all kind of so this is a really high performance interconnect that your computers have. Even your laptops have it. Most laptops have a PCI Express slot, which is where the Wi-Fi cards and all are plugged in. So if you ever kind of open and go into the motherboard, that is what you would encounter there. So bus is one way, but bus has a problem. What's the problem? Architecturally, with this kind of approach. Say it again.
Like only one person can ever.
Only one person can use it at any given point in time, right? So I have this thing running through my entire system, but only two people can, only a pair of communication can take place at that time. I mean, I can do some sort of a broadcast, but I'm kind of limited to one transaction at a time. So how can I improve it? And again, without going to the other extreme of running a wire between running a set of wires between every pair of clients. So what are different ways you can think you can improve this?
So like multiple buses.
Okay, so multiple buses, but will add to the cost obviously. But yeah, I can have multiple buses. So multiple buses, and in effect, conceptually, I have a multi-lane highway. Okay, so that's one. What else can I do? So let's consider the following analogy again from the physical world. Let's say there is a road, there are multiple buildings on it. And the analogy out here is that whenever there are people moving from building A, some building A to some building B, we are reserving that road. And so unfortunately, as a consequence of that, only one pair of building is connected at any given point in time. Is there a way you can imagine without creating additional roads, as you are suggesting, I can have, under certain circumstances, A and B can talk to each other and C and D can talk to each other? So from a circuit perspective, if you think of a bus as a pair, bunch of wires running, is there a way I can do something so that I can have two transactions going on it simultaneously?
I'm just a guess, but like pipeline maybe kind of.
No, pipeline would still be going to time something.
If two transactions are on like different parts of the wire, then they wouldn't intersect.
Good. And so how can I separate them out? Is there anything we have learned in the course where we can say I can? So you're right that if A and B are next to each other and C and D are next to each other, it's kind of stupid that I'm hogging the whole set of wires. So I can have A and B talk and C and D talk, and maybe I can do something to separate these things out, so cut the wire temporarily. So what can achieve that?
A tri-state buffer maybe?
Tri-state buffer, exactly, kind of tri-state, bi-directional tri-state buffer. So you can do some magic out there, or a pair of multiplexers. So essentially at select points, I can kind of create switches. And I open the switch, my bus segments into two. Okay? So we can do those kind of games. I can stick with the bus structure and essentially start permitting multiple transactions going on at the same time. Multiple transactions go over at the same time in wireless arena all the time. My computer is talking to the access point, and so is yours. So it's all about separating communication out so that we can have communications going on in parallel between different pairs of entities. So this way that he suggested is one of spatially segmenting the bus. In wireless, how do we separate communications? Why is my phone able to talk to, or my computer able to talk to the access point at the same time your computer does? What's going on there? Different frequency, so different parts of the spectrum. Unfortunately, we can't use that on chips very easily because we are not operating out in the radio frequency regime. It's all what is called as baseband signaling. So we don't really have that concept on the chip level, but there is some work which seeks to do that. So frequency is one. In wireless, space is also used, much like you were suggesting that there are multiple base stations and they're kind of separating things out. There's something, there are coding techniques which can help you separate things out. So a variety, and there is time. We take something and divide it up into tiny time slots, and we say every slot number I in a frame is yours, every slot number J is yours, and we kind of all live happily in that. So many of these techniques kind of carry over to the chip level as well. But that leads me to what I had started, what I had mentioned a while ago, which is this whole concept of a switch. So buses are not very practical in many settings because bus has to run past every building, so to say, right, that highway. And bus is complicated, so that makes a problem. But the other part, as we also realize, bus has these limitations that a single transaction can take place on it at any given point in time. So in networking and more generally I/O, the concept which emerged very early on, and which one can use on the chips also, is this notion of some sort of a crossbar connect, some sort of a switch. And whose job, what a switch does is it has a bunch of ports. So these are ports. And the clients, senders and receivers, connect to the switch via ports. So there is a wire or whatever, a cable or bundle of wires running from each client to the switch. That's the equivalent of the Ethernet cable running from the jack to the switch. Or in case of a chip, it would be some bunch of wires, data line, clock lines, and stuff like that, running from a client to this switch. Inside the switch, so the switch would have bunch of input ports and bunch of output ports, or maybe just a bunch of I/O ports. Okay, and what the switch does internally is that it gets all these requests. So at any given point in time, there's some client saying, "Hey, I want to send data in on." And internally, what this guy does is it connects things together. So in early telephone system, which is how this concept started, in the telephone exchanges, there were people, telephone operators, and when you would pick the phone up and attempt to make a call, then someone would go and literally have a wire running between the two who wanted to talk. So there were these patch cords, and they would go up and connect the two. That's how early telephone systems were there. Everyone's line goes to the central place, and they were there. And then human beings got replaced by electromagnetic stuff, and then by electronic stuff, and sort of now everything happens at much faster rate through hardware now. So these little boxes, switches, what they do is basically in time they figure out how to connect things together, and internally they can have more than a single bus. They can have more sophisticated stuff so that they can connect multiple simultaneous transactions. So a very common structure might be like the following. So imagine I have these kind of lines running from every sending thing, and these kind of lines running for every receiving one. And let's say sending client 1 wants to talk to receiving client n-1. Then what I will do is I will activate this little interconnect. So I have this crossbar structure, and just at the right points, I activate things for the duration. So with stuff like this, I can potentially have n conversations for n data exchanges taking place simultaneously. Of course, if two people want to talk to the same person, I'll have a problem. But I can have multiple independent interconnect connections going on simultaneously. So this clearly is performance-wise an advancement over the bus, because in bus we can do one at a time. Okay, now I can do potentially up to n at a time. And then equivalent of the arbiter is this allocator. So there would be this entity in there in the switch which takes account of all the requests which are coming in, and then does this magic to the this fabric, this cross connect that exists. I can have a full interconnect, or I can have sort of less capable hardware, depending upon what we are willing to, depending upon how much hardware resource we are willing to do. So this switch-based architecture is very common in networking, whereas bus-based stuff is what used to be the case on chips and boards. But now, because the performance requirements have been going up and up, and so we in recent 10 years or so, it's very common to have what, like I said, what they call as network on chips. So you see these kind of cross-bar switches and all. So FPGAs is one great example of it. If you ever look at a photo of an FPGA die, you would see that it has lots of pockets of logic gates which can be programmed, and then they have wires running in a Manhattan grid-like fashion, and lots of places they have these switches. And then I can take a piece of hardware and map it to one place, another piece of hardware and map it to another place, and I can tell my EDA tools, these guys need to talk, and they kind of arrange everything from that point on. So this crossbar switch is a powerful interconnect concept, and that in turn has led to a lot more complicated kind of things. There are very complicated interconnects that people now put on chips and all, much beyond the scope of this course. You will, if you do some grad level courses and all, you'll probably encounter them. They have hypercubes and blah blah blah, a whole bunch of stuff with nice mathematical theories inside them and all. They are kind of dealing with these things. Okay. Finally, memories. So in this course, we didn't talk much about memories at all, other than some brief references to it in the combinational module section, where I talked a little bit about the ROMs and stuff like that. So memories are as important a part of digital system as logic. So very broadly, there are three pieces to digital systems: logic, namely computing; memory, remembering stuff and all, so registers and stuff like that; and interconnect or I/O. The course mostly focused on the first one, but these other two are no less important. So memories, we saw, the dominant one we saw in this course are registers, flip-flops. They are memories. What are the other kind of memories in our systems? In our computers? What other memory technologies we encounter?
RAM, hard disk, cache.
Okay, RAM, hard disk, cache. What's the difference between RAM and cache?
Cache is faster.
Okay, but cache is also RAM. So, but you're right. So, hard disk, there is main memory, which is what I guess you meant by RAM, and there's cache. And usually nowadays we often have 2 or maybe 3 or even 4 levels of cache. Technology-wise, hard drives are magnetic or flash-based SSDs. Main memory is DRAMs, and in smaller computers might be so-called SRAM, static memory, static RAMs, and caches are almost always SRAMs, static RAMs. Main difference across this spectrum is performance versus density versus speed. Okay, so hard drives are most dense, but obviously a lot slower. SRAMs, which are used for caches, are least dense, very fast, consume a lot of power, so they sit at the other spectrum. And memory therefore gets organized as this hierarchy that farther out, lower down in the hierarchy we have bigger amounts of memory, and then a subset of that is kept at the next layer and the next layer. So registers have very immediate content, caches have next higher up, main memory even next higher up, finally the hard drive, and I guess finally your Dropbox or Google Drive or whatever kind of exists. But conceptually, all memory basically is about, I said Google Drive and it needs to quit. Okay. So conceptually, memory at any one of these tiers can be thought of as having an address and having some data. Hard drive is like that also. What are the addresses on the hard drive? Like how do we address a hard drive?
Usually like a hex code.
No, so they're all binary for sure, but I was just thinking that what is the concept of an address? So hard drives are rotating magnetic platters, and the address is the concept of sectors, disk sectors. Have you ever seen error messages about sector gone bad or stuff like that? So hard drive is essentially a sequence of bytes or sequence of bytes, and you can address them, and you address them in terms of which platter on a multi-platter hard drive, which sort of think of it a bunch of concentric circles, so which circle, and then which sector within the circle. So there's a whole addressing schema that exists, just like row and column for the memories that kind of I showed. So all these memories have address and data thing. The way they differ are these dimensions: capacity, bandwidth, latency, granularity. And since we have begun to max out on the hard drive side, there's search on for next generation of storage there, and likewise for on-chip memories also. So there's a lot of work going on things like on-chip magnetic memories and things like that. But the thing I wanted to point out was that probably the most common form of memory that you would encounter on chip, besides your flip-flop, is going to be SRAM, which stands for static RAM. And that's the fastest form of memory conventionally that we use. DRAMs, which is what the main memory on our computers are made of, they are much more finicky technologically. They require separate semiconductor processes. So it's relatively rare to find DRAMs sitting on the same silicon die as rest of your logic. IBM has something called embedded DRAMs, and they come with compromises. So essentially the message I'm trying to give is that silicon processes which are used to make logic are not the ones which are well suited for DRAMs and vice versa. And therefore DRAMs usually sit separately, but SRAM can be put on your chip. So you'll find sort of logic blobs with registers and stuff like that, and SRAM all on the same chip. Flash memory again requires a separate kind of process. Again, they are separate chips. You cannot have them on the same die. But what people do is that they stack dies in 3 dimensions. So they may create a DRAM and they may create a processor and then stack them up in a 3D structure. From the outside, it may look like a single computer chip, but inside there are multiple stacked stuff going on. So SRAMs, the nice thing is they're actually very easy to use. So at the SRAM level, all that happens is to read an SRAM, you put an address on the address line. There will be a signal saying I want to read or write, and so that's what is shown out here. These signals out here, and then the RAM will respond. So a typical thing might be I tell the chip that I'll say I enable the chip, so there will be some signal for that. I'll have some address lines. I'll have some line for read and write. And so if let's say I assert the read line, then the chip will respond with the data after a certain delay. And SRAM is pretty fast, but not as fast as registers. So registers respond in a single clock tick. SRAM might be several clock ticks, maybe order of 10 clock ticks, let's say. So much, still fast, but slower. DRAMs are the workhorse, the main memory. and these are the so-called DRAM DIMMs. And there are a whole bunch of standards for them and all, but so DRAMs sit on the motherboard, you plug them there. They are very finicky in multiple ways. So one of the ways they are challenging to use is that they need to be refreshed. That is, even if you are not using them, the data which is stored as charge and capacitors tends to decay. So you have to go through an act of refreshing them. There's a particular operation that you have to apply. And that takes time away. If you read a DRAM or you read a DRAM, then it automatically refreshes it. But if you are not, so somehow you have to arrange that every location in the DRAM is refreshed at a sufficiently fast rate, otherwise the data is lost. DRAMs are very dense. Again, so what's the largest DRAM DIMMs you think you currently buy? Anyone? No? You never buy memories for your computers? No? So they usually come 4-bit wide. They rare are the DRAMs which are, but yeah. You can have 256 gigabit on the high end. So these are what you see out there are multiple sort of chips. So each one of these would be a single DRAM chip, and then they're glued together. Oftentimes, you will find these are designed for an 8-bit parallel output. Each chip is 1 bit. Oftentimes, you may see a 9th chip out there. Why do you think it might be? Even though it's an 8-bit DRAM. Memory errors. So one of the bane of modern shrinking technologies is that bits are no longer very reliable. You store a bit and some of them are going to get corrupted for a variety of reasons, including something called alpha particles which come from space. And we are storing smaller and smaller amount of charge. When those particles hit the whatever pass through the memory cell, they flip them and all. So there is tremendous amount of error coding and those kind of operations which are done at the memory level to kind of cope with these kind of issues. So DRAM is the other primitive that we have. So let's see. Yeah. So the challenge that we face across all these technologies is that there's no such thing as cheap, dense, low power, high speed, all of them in one thing. And speed also presents the challenge that low latency, which is I issue a command, how quickly I get the data, and also what rate I can issue the command. So all those kind of issues come up. So as we discussed a short while ago, the way memory systems are organized are in forms of these hierarchies that I'll have DRAMs and then I'll have memories of different types, including caches and stuff like that organized throughout the system. So even on the chip, oftentimes you may have multiple banks of multiple memories in different hierarchy. One of the nice things when you are designing on the chip is that you can have multiple memories which you can talk to in parallel. A normal CPU has one pathway to the DRAM. But if you are designing a specialized computer system, you can have multiple banks of DRAM and talk to them simultaneously and do all sort of interesting stuff around those things. So this covered kind of the other aspect of digital systems, which we didn't talk much about. Again, so memories and interface and interconnects. Some of the more advanced courses here at UCLA kind of touch through them, go through them at the grad level in particular, but also the computer architecture class, which follows this course, is one where again you go deeper into some of these issues. So with that, I'm at the end of the material that I want to sort of cover. So all through the material this week is part of the finals. Anything I talk about on Tuesday is not. You are welcome to not show up, or fine. Thursday, if you are, if none of you are showing up, then I guess I'll just go back. But in any case, on Thursday we'll do a review. I don't know how many of you are in favor of doing a review on Tuesday instead of Thursday. Relatively few, so I'll stick to Thursday. Okay, so Thursday we'll do a review, and then remember the final exam is at some ungodly hour in the evening on Monday. And TAs will go through again more review stuff next Friday. But again, everything up to now is in course, is in obviously sort of stuff which is post from finite state machine onward. The emphasis is going to be more on that. Stylistically similar to midterm, you can expect one of those questions which surprisingly several students do it, which is a question number 1 where I just rapid fire short questions on a whole bunch of things. And then there will be a few different questions. It's a longer exam, it's 3 hours as opposed to 2 hours. Same kind of thing, cheat sheet, except that this time around you can bring 2 pages. So total of 4 sides, 8.5 by 11. So this way you can perhaps just, if you want, you can just bring your midterm cheat sheet and just prepare a new one for this part of the class. I don't know. Any other questions? No? Yeah.
What kind of questions we should expect from today's lecture?
General conceptual kind of stuff. So I guess I'm a big fan of students in engineering being curious about technology. So yeah, so general familiarity with what are these things. I mean, if you're studying to be a computer scientist or electrical engineer, you should be familiar with these things which are almost part of our modern society in terms of these terminologies and all. So that would be the kind of stuff. Okay? By the way, these are also book chapters, so you can just do a read.
Is there an emphasis on stuff after the midterm?
Yeah, I said that, right. But when I'm taking the word after a little bit liberally, because finite state machines get covered before the midterm also and after the midterm, so they're part of it. But it really, frankly, doesn't help you much because you cannot do sequentials without combinational, and so pre-midterm was combinational, so essentially the whole course in a way. So, okay. Any other questions? One other thing I've been told to remind you that you should probably have received emails about evaluating the course, so make sure to do that. And feedback is always extremely valuable. If there is other feedback you want to provide to me directly, anonymously, whatnot, feel free to certainly welcome that. Let's see. Homework 3, we'll hand out the solutions to everything prior to the final so that you have access to that. Homework 3, I'm hoping will get graded by then. Homework 4, those of you who are planning to do it, will most certainly not be graded prior to the finals, but we'll hand out the solutions for sure. Design assignment 4, I don't know how many of you have decided to back off from it versus doing it. I know several of you are. Remember, you have to do that in-person thing on next Thursday or Friday. So we'll post a set of slots, plenty of slots. You have to sign up for it. Ideally, both partners would show that would be great, but even if one of you shows up, that's fine. One other thing I also wanted to mention was the following. I have had a couple of requests of the following nature, and so one request was I ran out of my late days. And the proposal was, can I zero out a prior homework and recoup the late days? Okay, because perhaps you scored very low on a prior homework and you think it's worthwhile to gain additional late days, and let me give you a 0 score on that prior homework. That's fine. You need to contact me on that, okay? Because if you're hoping that you can do better on the current homework. Okay, so that's one part. Late days itself, I'm going to most likely put up the sheet up. I think many of you have plenty of kind of late days left, so to get rid of that, let's see what other thing I want to tell you. Yeah. How many of you are doing design assignment 3? Okay, fair number. Okay, cool. Okay, so I'll see you on Tuesday.